In this video, we will discuss about why we select microstrip patch antenna, calculate the antenna design parameters using design equation, and design a rectangular patch antenna using HFSS software, then analyze the result. Next, we have to introduce some enhancement technique, then compare the results. Why we select microstrip patch antenna? Microstrip patch antenna is easy to fabricate and capable of operating in multi-bands. The performance is high and low weight, low cost and low size. Microstrip patch antenna is polarized in both linear and circular polarization, and impedance matching is also simple. Application of microstrip patch antenna. This is practically used in microwave frequencies, GPS, mobile satellite communication, biomedical fields, wireless LAN, WiMAX. Calculate the antenna design parameter using design equation. Before designing an antenna, we consider three parameters. First one is resonant frequency, F0, substrate height H, and dielectric constant of the substrate is epsilon r. In first step, we have to calculate the wavelength, lambda equal to c by f0. F0 is the frequency, c is the speed of light. In second step, we calculate the width of the patch antenna. This is the equation of patch width. Next, in third step, we calculate the effective dielectric constant. In this equation, we have to substitute the h and w value and calculate the effective dielectric constant. After calculating the effective dielectric constant, we have to calculate the length L. The patch length is calculated from the below equations. After calculating the patch length and width, we have to calculate the substrate width Ws. Ws equal to W plus 6 into H. Calculate the substrate length Ls as found. Next, substrate length Ls equal to L plus 6 into H. Using the above formulas, we have to calculate patch length, width, substrate length, width, and lambda value. Here we use the full ground plane, so the length and width of the ground plane is same as compared to the substrate length and width. First, we design the antenna from bottom layer to top layer. The bottom layer is ground plane and the middle layer is substrate and the above top layer is patch. The feeding is placed bottom or top layer depends upon the feed selection. Here we use insert feeding technique. This is the feed with length and insert distance and insert gap. The insert feed with length and the insert distance gap value is given below. Using these formulas, we have to design the antenna. Design a rectangular patch antenna using HFSS software. Now open the HFSS software. This is the front view of HFSS software. In left corner, menu bar is there. This is the ribbon tab. In this ribbon tab contain desktop tab, view tab, draw tab, menu tab, simulation tab, result tab, and automation tabs. This is the project manager window. In this window contains all the details about the project. This is the property window. This is the message manager window. In this window, display the information about the simulation, error, and warnings. Next, progress window. This window monitors simulation process. Now create a new project. Go to project menu bar. Select insert HFSS design. Before we designing the antenna, we have to add the antenna parameters. To adding the antenna parameters, go to HFSS or HFSS 3D layer and select design properties. The property window will appear. Now click add. The property window will appear. Here enter the variable name L, unit type as length, enter the patch length 29 mm and click OK. Likewise, we have to add all the parameters. After completing the parameter initialization, we design bottom layer, that is ground plane. To design a ground plane, click Draw tab and select the 3D cube and randomly pick the starting and ending point of the object. Now double click the box. The property window will be open. In that window, we have to enter the object name as ground. Next, select the material row. The material library window will open. In that window, resolve PEC and select PEC. Click OK. If you want to change the color and transparency value, change and click Apply and OK. Now to fix the length and width of the object, double click the Create Box. The property window will open. In that window, we have to enter the position of the object. For entering the position value x, y, z, starting point, that means minimum point of the object. Here the x position value is minus ws by 2, y position value is minus ls by 2 and z position value is 0. Next, the total size of the ground plane is ws and y size ground plane is ls and z size of the ground plane is t. Now we design the bottom layer. Go to draw bar and select 3D cube. The starting and ending point of the object is selected randomly. In this property bar, we change the object name as substrate. Next, click the material row. The material library window will open. In this library, we search FR4 substrate, select and click OK. Now to fix the length and width of the substrate, double click the Create Box. The starting position of the substrate is minus ws by 2, minus ls by 2. If the position is t, the x size width is ws and y size length is ls and z size is h. Now we design a middle layer. Next we will design a top layer. As for designing the patch, select the 3D cube and randomly select the starting and the ending point. Enter the object name as patch. In material, we select pick, color as yellow and click Apply and OK. Now to fix the length and width of the patch and double click the Create Box. X position is minus w by 2, minus l by 2 and z position is t plus h. The x size is w and y size is l and z size is t. And click Apply and OK. Next we design the feeding line. Draw the 3D cube, double click the box and enter the object name as feed. Select the material as spec, Apply and OK. Now we fix the length and width of the object. Double click the Create Box and the property window will be x position is minus wf by 2 and y position is minus ls by 2 and z position is t plus h. X size of the feed line is wf and y size is lf and z size is t. Click Apply and OK. We design the insert feed. Double click the box and rename as insert feed. Select the material as and change the color. Apply and OK. Double click the create box. The property window will open. In this window, we fix the position of the insert feed. The X position is WF by 2, the Y position is minus LS by 2, and Z position is T plus H. X size of insert feed is G, and Y size of insert feed is D and Z T. Click apply and OK. Click the insert and go to mirror duplicate and pick the center position as base point. Drag the object in X direction. Then select the duplicate mirror object and the property window will open. Here we mirror the insert part in X axis. So put -1 in X plane. -1, 0, 0 and click apply and OK. Then select the patch and subtract the insert and insert one. Click subtract option. The subtract window will open. In this window, the blank part is patch and tool part is insert and insert feed, and click OK. Now select the patch and feed. Go to draw tab. Select unite option. Now save the project. We will assign the port. For assigning the port, go to draw tab and select grid as XY plane and pick the 2D draw box and draw a rectangle. Now double click the rectangle and change the rectangle as port, and if you want to change the color, click apply and OK. Now to fix the length and width of the port, double click the create box, enter the starting position as -WF by 2, -LS by 2, Z position as 0. Next the X size is WF and Z size is T plus H plus T. Click apply and OK. Now the port will assigned. Now select the port and right click the port, select assign excitation. Here we select the lumped port. The port impedance is 50 ohm and click next. In lumped port mode window, select the integration line as new line. Now pick the rectangular box bottom end to top end. Click next and finished. Now the port will assigned. Now we assign the boundary conditions. Right click the patch and select assign boundary. Select perfect E and OK. Next assign the boundary as ground. Select assign boundary. Click perfect E and OK. After assigning the boundary condition and excitation, we'll design an air box. Go to draw tab, select 3D cube shape, randomly pick the starting and ending point of the object. Enter the object name as air and click the material row. And in that library window, we search the air and select air and OK. If you want to change the color and transparency value, and change and apply, then click apply and OK. To fix the air box value, double click the create box. The starting position of the air box is minus lambda by 4 minus ws by 2 and y position is minus lambda by 4 minus ls by 2 and z position is minus lambda by 4. Next, the air box x size is lambda by 2 plus ws. Y size is lambda by 2 plus ls and z size is lambda by 2 plus h. Now we assign the radiation boundary. Right click the air box and select assign boundary. In that assign boundary, select radiation, click OK. Next we set the solution setup. Right click the analysis on the project manager window and click the add solution setup. In that select the advanced option. Here we enter the frequency value as 2.4 GHz and the number of passes is 20 and click OK. In that window we select sweep type as discrete and set the frequency range from 1.5 GHz to 3 GHz and click OK. Next we set the far field setup. Right click the radiation in project manager and select insert far field setup. The infinite sphere box will open. Here we set the pi value as 0 degree to 360 degree with a step size of 2 and theta value starting from minus 180 degree to plus 180 degree with the step size of 2 and click OK. Now the designing part will open. Go to simulation tab, check validation, then analyze all. The simulation is over. Right click the result in project manager, select the model solution data report and select the rectangular plot. Here select the category as S parameter, quality as S11 and the function is dB and click new report. The reflection coefficient of the antenna is plotted here. The acceptance value of the reflection coefficient is minus 10 dB. Now the operating frequency is 2.4 GHz with the reflection coefficient of minus 22 dB. Now we analyze the VSWR function dB. VSWR is the ratio between the transmitted and reflected voltage standing wave in the transmission system. Here x-axis is a frequency, y-axis is a VSWR. Here the antenna operating at 2.4 frequency, the VSWR value is 1.159. Right click the result in project manager and select the far field report. Here set solution type is sweep. Primary sweep is frequency. Theta value is 0 degree and pi value is also 0 degree. Now we select gain in category 12, gain total in quantity and select function as dB. Click new report. The gain plot will open. Here the antenna operating at 2.4 GHz with the gain of 2.1 dB. Next we will analyze the directive. Right click the result, select far field report and select rectangular plot. Set solution as sweep, primary frequency sweep and click families. Select theta value is 0 and pi value is 0. Now select the category as directivity, quality is direct total and function as dB. Then click new report. Now we plot the directivity graph. The antenna operating at 2.4 GHz with a directivity of 5.8 dB. Next we plot axial ratio graph. Right click the result, select far field report, set solution as sweep, primary frequency sweep and click families. Select theta value is 0 and pi value is 0 and click category as axial ratio, function as dB. Click new report. The antenna operating at 2.4 GHz with the axial ratio of 57 dB. Result analysis. In existing method, the S parameter is plus minus 22 dB. VSWR value is 1.15. Gain of the antenna is 2.1 dB. Directivity is 5.8 dB and axial ratio is 57 dB. Next we introduce some enhancement technique. Here we use circular polarization technique. Circularly polarized antenna radiates E-field energy in both horizontal and vertical plane. That means it radiates in all directions. Here it has two linear electrical field components which are perpendicular to each other with same amplitude at 90 degree phase shift. Based on the E-field rotation, it is classified into two types: right-hand circular polarization, left-handed circular polarization. Why we go for circular polarization means interference is less, losses are minimum because it's transmitting in all directions. Polarization adjustment is not required. How to achieve the circular polarization? There are many ways to achieve circular polarization. Some techniques are use cross dipoles, truncating the patches, stubbing the patch, introduce slots in patch. In proposed work, the proposed antenna circular patch is used instead of rectangular patch. The circular patch is optimized to get the desired frequency. To reduce the cross polarization, the coaxial feeding technique is used. The main advantages of feeding technique is best impedance matching, because feed can be placed at any position. See, this is the proposed antenna. Here the circular patch is used instead of rectangular patch. The feeding technique is used as coaxial feed. The proposed antenna is parameter VSWR and axial ratio plot is a result comparison. Antenna operating at 2.4 GHz, S parameter value is minus 37 dB, VSWR is 0.33 and the axial ratio is 1.76 dB. Axial ratio is defined as the ratio of maximum axis and minimum axis of the antenna pattern. If the axial ratio value is 0 to 3 dB, the antenna operating in circular polarization. If the axial ratio value is 3 to 10 dB, it operates in elliptical polarization and the antenna has a linear polarization. Then the ratio is more than 10 dB. Here the axial ratio is 1.76 dB, so the proposed antenna radiates in circular direction. Reference: this technique is referred by the Antenna Theory book authored by Balanis. Hope this video is useful to design an antenna. Thank you.